Okay, so Rob is going to do the official welcome, but I just have one or two small announcements. So one is that in the evening today at 5:30 we have a discussion about publishing in math with Jonathan Walls. And then after that at 7 is the banquet, which is at the hotel at the Hilton. If you want to come to the banquet, if you're registered for the banquet, but you haven't paid it, then please during one of the breaks, you will still all in and sign up for it. Also, we have the schedule for the entire AGNES meeting outside on the big monitor, but unfortunately the monitor is too short. It's a very big monitor, but it's still not long enough for the schedule. So the last talk on Sunday is cut off. It's like cut off after Professor Nakashima's talk, but in fact there's another talk by Juliana Tomowsko. So that you cannot see that on the schedule, it's on the schedule.
No way to scroll down.
You need to get a hold of one of the Simon centers. Yeah. Well, we can try it. Okay. Oh yes, and then out of politeness, I also need to remind you that the general policy in this auditorium is no food or drink. Okay. Okay, so with that, I will hand it over to our chair, Rob Lassersfeld.
Well, yesterday, Sasha Aminoff welcomed everybody on behalf of the Simon Center. So I want to welcome everybody on behalf of the math department. Sasha said a little bit about the Simon Center. So for those of you who are new to the math department here, there's a lot of algebraic geometry in the math department. And in fact, there's a deep connection with AGNES. So our colleague Jason Starr was one of the, if not the founders of AGNES. And so we're happy to host it once again. For those of you who are here for the first time, I hope you'll keep in touch with us and come back. Like the Simon Center, we have postdocs. We have joint postdocs with the Simon Center. So in any event, we hope you enjoy your weekend at Stony Brook. And I'll turn it over to Antonella, who's chairing this morning's session.
Okay, thank you. And the first speaker is Lev Borisov from Rutgers and the Institute. The title is really nicely written here. If you cannot read it, move forward.
Thank you for the invitation. It's a great pleasure to speak to such a large audience. I'm going to talk about a relatively simple construction that I stumbled upon by accident about 3 years ago. And there were some developments since then. It has something to do with the Grothendieck ring of algebraic varieties, which I need to define first. So for me, for the most part, I'll be working over complex numbers. That's my preferred domain. So this is what I'm going to try to define, the K0 of varieties over C. Known as the Grothendieck ring, and it's defined as follows. You look at formal linear combinations of algebraic varieties, or maybe isomorphism classes of algebraic varieties with complex coefficients, with over complex numbers, complex algebraic varieties, and these are linear combinations with integer coefficients. They're going to be finite linear combinations. Well, as it is, that's just boring, so that doesn't really make any, it's really not of any interest. But what you do is you take a quotient of this free abelian group by the span of certain relations. Basically, it's a span of a cut and paste relation. For every variety X with a closed subvariety Z and the complement U, you declare X to be the sum of U and Z. And so Grothendieck ring is whatever you get by taking the quotient over the span of these relations. All right, I advertised it as a ring, so I better produce multiplication. to multiply x and y, you multiply x, you do Cartesian product of x and y. So this notation means that this is an element of the Grothendieck ring which corresponds to the variety x, and the product of two generators corresponds to the Cartesian product. And it's not so hard to convince yourself that it's compatible with the relations, that you don't get into trouble modular relations. There is an identity which is just a class of a point. I'll just call it 1. All right, so far so good. Let's do some examples to get a little bit of more comfortable with this ring. So first, let me introduce this L. Stands, I guess, for something like Lefschetz. And it's a class of affine line, or maybe stands for line. I mean, it depends what you want to think of it. So what else do we know? The class of C to the n, by definition, is L to the n. Fine. The class of CPN. Well, CPN has a closed subset, which is CPN minus 1, with the complement being Cn. So by our relation, you have class of CPN minus 1 plus L to the n. And if you repeat it enough times, you're going to get 1 plus L up to L to the n. So it's some kind of polynomial in L. All right. What else? How about G24, the Grassmannian of two-dimensional subspaces inside a fixed four-dimensional space, or if you wish projectively, the space of lines in P3? Well, it has a Schubert cell decomposition, so it is a union of affine spaces, locally closed subvarieties of various dimensions. And so again, you get something like L to the 4 plus L cubed, some polynomial in L. Let's do something non-compact, the class of C star. So the non-zero complex numbers. Well, it's you take complex numbers and then you remove a point. So you're going to get L minus a point. Well, not everything is a polynomial in L. If you take some kind of elliptic curve, doesn't matter which one, then the class of that is not a polynomial in L. I mean, that's not terribly difficult to show, but I don't want to explain why just yet. What else do we want to know about the Grothendieck ring? Well, there's the following very useful observation. If you have some kind of fibration, let's say S mapping to X, and suppose this is Zariski locally trivial, with fiber Y. Then in this case, the class of S is the product of x and y. Well, that follows from the cut and paste relation, so you can just chop up x into pieces over which you have true products, and then you do inclusion-exclusion for the intersections, then you arrive at this result. Now, for example, if you have blow up of P2 at a point, then this maps to P1 by projecting from that point, from P2 from that point, and the fibers are P1, so this is one of the Hirzebruch surfaces. And so you see that the class of this blow up is the same as class of P1 times itself. So the base is P1, the fibers are P1. So it's also the same as the class in the Grothendieck ring, which corresponds to simply P1 cross P1. So in no way do you expect the Grothendieck ring to classify varieties, but it's still an important invariant of varieties. So how should we think of it? Well, if we were not over complex numbers, but say over a finite field, then this kind of relation could be thought of as maybe some kind of counting points. Right? If you could count points on x, then that would be as many as on u plus z. Okay, we're in over complex numbers, so we cannot count points in a good way. So the analog would be Euler characteristics. And specifically, Euler characteristics with compact support. So this invariant can be recovered from the class of x. More generally, what can be recovered is something known as a Hölderlin polynomial. And if you know what it is, great. If you don't, it's just kind of a preview of something. So for compact smooth algebraic varieties over complex numbers, this is just a gadget that encodes all the Hodge numbers. If your variety is singular or non-compact, then you need to talk about mixed Hodge structures, but that's a whole different story. But nonetheless, there is an invariant that can be recovered again from the class of x. You can recover even more. I mean, somehow, whenever you have this type of situation, there's a long exact sequence of mixed Hodge structures. So you actually get a little more than just numerical invariance out of the Grothendieck ring. But this is not so important. All right. As one may expect, this K0, this Grothendieck ring, is a very complicated ring. Because essentially anything you say about that ring is saying about something about all the complex algebraic varieties. And to give you the first example that shows its complexity, is an example due to Punin. And it shows that this ring has 0 divisors. So what Punin does, he produces 2 surfaces, x and y. They are smooth projective surfaces. They are abelian surfaces, to be more precise. So some kind of 2-dimensional analogs of elliptic curves. And they have the following interesting properties. On one hand, x is not isomorphic to y. And on the other hand, x cross x is isomorphic to y cross y. So when you have this x cross x equals y cross y, you convert it into equality in the Grothendieck ring. And so you get this product being equal to 0. And it is not overly difficult to show that both of these factors are not 0. This one simply follows from that Hodge-Deligne polynomial, whatever it is. This one is a little more subtle. He has to look and see that the Hodge structures on x and y are different, but it works out. All right. I don't remember what the date on this example, but I want to say maybe 80s or 90s, so it's a fairly old example. Couldn't be the 80s. Okay, 90s then. Okay, no, I agree. Shouldn't be the 80s, yeah. You never know, though, right? Yeah, well, no, but it is possible. Okay. All right. So, in 2014, inspired by some joint work with Anatoly Lipgober and also by a preprint of Galking and Schinder, I proved the following, that L is a 0 divisor in the Grothendieck ring. Now, that's a little bit more unexpected, because L is such a fundamental thing. You know, it's a multiplication by a line. So, how does that come about? So the construction involves finding 2 varieties, x and y, which are 3-dimensional, projective, and Calabi-Yau. And what you can tell about it is that the class of x is not equals the class of y. And on the other hand, the class of x minus class of y is annihilated by the 6th power of L. To be historically precise, I had a weaker statement. I had L squared minus 1 times L squared minus L times L to the 6. But then there were further improvements by Kuznetsov and Chamberlain. I'm not sure how to pronounce it. And then Martin. And that's the published version that has the L to the 6. So today what I'm going to explain is the geometric construction that gives you that result. It's going to be very close to an actual proof. The beauty of it is that the whole paper was 5 pages. So it's not a very, well, it wasn't a very complicated thing based on what was already known by the time. Because it does so the proof that class of X is not equal to class of Y, that's actually rather difficult. And that only is known in characteristic 0, because there are some technical tools missing in positive characteristic. But the equality is a geometric construction, and that's simple enough so I can even put it on the board today. We're okay so far? Okay. So let me get to the construction. You start with a vector space V, which is 7-dimensional. And then we pick a 7-dimensional space of skew forms on V. So there is this H2 of V dual. This is 21-dimensional vector space. And inside of it, we pick a 7-dimensional subspace. And we pick it generically. If you don't, so there's a risky open subset inside the Grassmannian of 7, 21, where we want to pick our W. If you want to be specific, we'll pick W so that all the coefficients mutually transcendental over Q or something. That should certainly do it, but it doesn't have to be that bad. So just a generic W will work. And so, all right, so we have the 7-dimensional space of skew forms on V. And so out of this data of V and W, I'm going to construct 2 Calabi-Yau varieties, X and Y. They're indexed by W, so I'll call them X, W, and YW. So for different W's, you get different ones. All right, and I will move to the other board. All right, XW first. For each 2-dimensional subspace of V, so this is just a vector subspace, and each skew form in my capital W, consider the restriction. So W restricted to T2, think of it as an element of H2 of T2 dual. That's a one-dimensional space. So for every W in my space of skew forms, I can restrict it to any two-dimensional subspace of V, and it's either 0 or not. Right? This is a one-dimensional space, right? Skew forms on a two-dimensional subspace. This is a one-dimensional space. And then I'm going to define XW to be the set of all such T2. Now I'm going to think of them as points inside the Grassmannian of two-dimensional subspaces of V, such that for all W's in capital W, the restriction of that W to T2 is 0. How can I think about this geometrically? Geometrically, you have Grassmannian, G2V. It's a 10-dimensional space. And then each of the basis elements of capital W gives a hyperplane cut of it, or gives a cut of it, a hypersurface cut of it. And so this XW is a complete intersection of 7 Luker hyperplanes, hyperplane cuts of the Grassmannian. And the condition on W that I needed is that the intersection is transversal. So that was the condition. By Bertini, it happens on the open subset of the Grassmannian. All right. So if you know your adjunction formula, you see that XW is a Calabi-Yau. What this means is that the canonical class of XW is 0 in the additive notation. So the exterior power, a third exterior power of tangent or cotangent bundle is a trivial line bundle. What about YW? Let's look at another interesting feature of this situation. For a skew form on a vector space, there's a concept of rank. Moreover, the rank of the skew form is always even. That's a general statement. So in our case, the ranks could be 0, 2, 4, and 6. So 0 only happens when W is equal 0. And for W that are non-zero in capital W, we may assume that the rank is either 4 or 6. By may assume is if we pick our space capital W generic enough, then it's going to miss all the rank 2 forms. And then YW by definition is going to be a subvariety in the space of lines in W. So in the projective space P6, remember W was 7-dimensional. And is defined as lines through W's of rank 4. It is a little less obvious. Well, it certainly requires more sophisticated computation to show that this is a Calabi-Yau. And it was done by, certainly it was published by Rutgers in around 98. And this, the statement that YW is Calabi-Yau of dimensions 3. So I mean, this is one specific example of Calabi-Yau varieties. So what's so wonderful about it? I mean, why is it interesting? If you've heard of mirror symmetry, then you can say that XW and YW are related by the following statement. The family of X's has a mirror family, and the family of Y's has the mirror family, and those mirror families coincide. So X's and Y's, they're not mirror to each other, but they have a common mirror. So that makes them very much related to each other. And in fact, the following has already been known. And this was my work with Caldararu. Where did I put this? At least here, but I think more. But no, I mean, it's this, right? Whatever. Let's just do this. Let's just not write. That's okay. Rodland somehow I remember, but my co-author I don't. Sorry. And also in parallel by Kuznetsov, the derived categories of coherent sheaves on XW and YW are equivalent. So this is an example of three-dimensional varieties which they're not isomorphic to each other, they're not even birational to each other. But nonetheless, they have the same derived category. And now, after this construction I'm going to put on the board, you also see that they have very similar, but not quite the same, elements in the Grothendieck ring. Okay. Now let me get to the actual construction. It's going to be slightly sketchy, but not terribly. The key to this is the following 15-dimensional variety. It's going to sit inside the product of G2V cross PW, and it's going to be defined as the set of pairs T2 in the Grassmannian and CW in projective space of lines in capital W, such that the restriction of W to T2 is 0. Not really introducing any new geometric ideas, but just repackaging this kind of condition. So instead of looking for the subspace in the Grassmannian of all those spaces on which everything from capital W restricts to 0, I'm just going to look at all pairs where the restriction is 0. Yeah. If you didn't, you don't need to think about it too hard. Actually, if you pick a generic 1,1 line bundle and this generic section. So if you pick a 1,1 line bundle and a generic section, that's your HW. So it's a very simple, really, varieties as algebraic varieties go. And then you have the following picture. This is HW of dimension 15. And it has two projections. It has projection on PW, and inside of PW there is YW. It also has projection to the Grassmannian, and inside of it there is XW. So Grassmannian has dimension 10, PW has dimension 6, and all of these guys, the loci inside, there is three-dimensional. And the idea is to calculate the class of HW in terms of the two projections. Think of it as counting points by kind of vertically versus horizontally, the usual deal. So calculate the class of W using two projections. The class of HW using two projections. All right. As always, one is easier than the other. The projection onto Grassmannian is easier, so I'm going to present that first and in a little more detail. And the other one is where some technicalities lie. So projection to the Grassmannian. All right, so suppose I have a point in the Grassmannian, and I want to see what lies above it. So it says fix T2 and look for all small w, CW, which have restriction to T2 being equal to 0. Okay? So the fiber over T2 is the following. So if T2 sits inside XW, well, if T2 sits inside XW, then every small w restricts to 0. So in this case, the fiber is simply PW, P capital W, because everything restricts to 0. So that's a P6 fiber. Well, what about outside? If T2 doesn't belong to XW, then the fiber is going to be also a projective space, but one dimension smaller. And moreover, outside of XW, the fibration is Zariski locally trivial. Because you really have a vector bundle, the annihilator of the So the kernel of the restriction to T2, it's a vector bundle of outside XW, and P5 is just P of that. So you have Zariski local triviality. This allows us to calculate in a very natural way the class of HW in the Grothendieck ring. And so what do you get? You get P6 over XW. And then you get P5 over the complement. But the complement is simply the class of G2V without XW. And so you get XW times the difference of P6 and P5. And plus some rather not interesting terms, P5 times G2V. This is some kind of polynomial in L. You can write it explicitly, but there is no point. But what you have over here is XW times L to the 6. And that's where that L to the 6 is coming from. So something like that. Some kind of explicit polynomial in L that is going to eventually cancel. And then the interesting part is XW times L to the 6. So in other words, by looking at this projection, you can see the class of XW in terms of class of H because the fibers jump over XW. Much the same thing happens on the other side. So when you take projections to the P capital W, what happens is the following. So fibers of the projection of HW to PW are the following. The isomorphism class of the fiber depends only on the rank of the form. So over CW of rank 6, you get a hyperplane cut of G27, G2V, I'll write G27, by a generic Plucker hyperplane. They're all isomorphic. And if you have a rank of rank 4, then you get the same thing, but it's cut by a hyperplane of rank 4. So it's some slightly singular cut of the Grassmannian. If you had the risky local triviality, then you could write the following. HW equals, well, by the same token, you'll have YW times the difference between the classes of rank 6 cut and rank 4 cut. Plus, actually the other way around. So it's rank 4 over YW. So that's the change. And then plus the class of P6 times the class of rank 6 cut. You don't have the risky local triviality, or at least not obviously, but what you do have is something slightly weaker but still sufficient. Piecewise, the risky local triviality. So what it means is the following. You take, if you have a family of skew forms over some base, then you can take the generic point of the base, so basically over a field of rational functions, you can put any skew form in a standard basis, and that'll give you the risky local triviality of a large open subset. And then it's going to be a complement of perhaps several components, but you can repeat the process and you keep getting the base split not into open subset on which you have local triviality, but on locally closed subsets in which you have local triviality. And that's enough for the Grothendieck calculation. So this is the observation of Chambellois and Martin, and that, and then was very disappointed that I didn't see it myself, but because it's a very natural thing. But after that, you just have to calculate these cuts, and that's pretty straightforward. And then you end up with the same result. So you get your HW equals class of YW times L to the 6 plus again some polynomial in L, which turns out to be the same by explicit calculation. So, okay, you put all of it together, and you get this formula. So you get this formula that the class of XW minus the class of YW times L to the 6 is 0. So, I mean, this is kind of a general theme. If you want to prove that something is 0 in the Grothendieck ring, it's a construction. If you want to prove that something is not 0 in the Grothendieck ring, well, that can get kind of hairy. So how does one prove that this difference is not 0? Well, that actually requires a fair bit of work. Fortunately, by the time I got to it, this was all well understood, and you can just quote a few strong theorems. But that's where the difficulty lies. It actually is based on several rather non-trivial statements. So the first statement, which kind of tells you that you have hope here, because otherwise it may seem hopeless. How do you know that you cannot put it in some higher dimensional varieties and do cut and paste and this and that and just get it without L to the 6? Like, for example, if you ask me, can you get it with L to the 5? I'll have no idea. I don't even know if you multiply it by L, if it's 0 or not. And I don't even want to speculate. Maybe it's 0, maybe it's not. But there was a paper of Larsen and Luntz, and they based their argument on something called weak factorization theorem. So weak factorization of birational morphisms. By Abramovich, Vladarchik, Matsuki, Karu, in some order. This is a big theorem. It works only in characteristic 0, which is where I need characteristic 0, that every birational map is decomposed into products of blow-ups and blow-downs. And that gives you enough control over the Grothendieck ring to surprisingly describe the quotient by L in a very simple form. So if you take the Grothendieck ring and you take the quotient by the ideal generated by L, then this has a basis, it's a free abelian group with a basis given by classes of projective varieties up to stable birational equivalence, whatever that means. Yeah, in fact, it's quite, I mean, I view it as a quite, it's again, it's a simple, so to go from weak factorization of birational morphisms to here, that's, 5 pages. Weak factorization is, what, 40 pages at the very least? So it's a significant, and it's based on Hironaka, which I guess has been improved to maybe only 60 pages by now. So this is difficult, okay? So you can hope now. You see that the difference is non-zero so long as xw and yw are not stably birational. And then again, you get a little bit of machinery that argues that if if these were equal to each other, that would imply that they are stably birational. So maybe I should say what stably birational means. So birational is when the fields of rational functions on them are the same. Stably birational is that if you attach a bunch of free variables on one side and a bunch of free variables on the other side, they become isomorphic afterwards. There is a work, I believe, of Kolar and Miyaoka, who say that if Calabi-Yau varieties are stably birational, then they are actually birational to each other. So I think, so this is because from the Calabi-Yau condition. Then there's a further statement that in dimension 3, birational Calabi-Yau varieties are connected by a sequence of flops. And these guys happen to be have one-dimensional Picard group, rank 1 Picard group, so they have no flops. So they would have to be isomorphic. So the point is that h11 of x is h11 of y is 1. And okay, to show that they're non-isomorphic, well, that I can do. They're non-isomorphic because they have even different topology. If you pick the generator of the H2 of Z, so the generator of the Picard, its cube on XW is 42 and on YW is 14. So there. So you get contradiction. So therefore, their elements in the Grothendieck ring are different. Okay, so this is one example, but as is often the case, once you find one example of a phenomenon, you realize that that there are lots more of them. So let me briefly run through a few other related constructions. I mean, I tried to do archive search. I'm not that good at it, so it's possible that I'm missing a couple of them. But hopefully not too many. Further examples. Let me get a new chalk. So the group of Japanese, Ito, Miura, Okawa, and Ueda, constructed examples where you have x minus y times L equals 0. And again, x and y are not Calabi-Yau threefolds. And again, they're not birational to each other. I think, again, it's Picard 1. And what are they? They are cut out from so-called G2 Grassmannians. So Grassmannians for the algebraic group G2. And you have this result. Then you have a result of Kuznetsov and Schinder. Yeah, and some of it is published, some of it is just preprints. So you have this equality for some, countable many families of case-free surfaces. Then you have the same group of people getting this identity for some other case trees. And then Hassett and Lai, for the same example, improve it to x minus y times L equals 0. So same example. And there's also a joint work in progress of mine, Andrei Calderaro, and Alex Perry, where we prove that x minus y times L to the 4 equals 0 for some Calabi-Yau threefolds. So these guys are intersection of two copies of G25 inside P9. All right, so these are the ones, the further extensions that I know about. There's been a fair bit of speculation for why in all of these examples you get Calabi-Yau varieties. There is no a priori reason that I know of that the zero divisors in the Grothendieck ring have to come from Calabi-Yau, except that the Calabi-Yau varieties seem to be the most rich area, for various counterexamples, and so that's just sort of a coincidence. Another thing is, in all of these cases, there are derived equivalences associated to the situation, and I don't have any strong argument for why derived equivalence should lead to something in the Grothendieck ring. And in fact, I suspect that it's just partly a coincidence, so some derived equivalences do and some don't. Physically, all of it is related, I believe, to something called non-abelian gauge linear sigma models. But anyway. All right, I think now that's a good place to stop, and I'm pretty much out of time, so thank you.
Any questions?
Yes?
What the Picard rank being 1, is that a general condition or a very...
No, it's a specific to x and y, to this xw and yw. I mean, you can see it for the Grassmannian, because the Grassmannian has Picard rank 1, and when you do complete intersection, by Lefschetz hyperplane Picard rank stays 1. For yw, it's not so obvious, but you can verify it.
Is the Calabi-Yau appearing in the other examples? Is it being used for the same sort of thing, or is it different things?
In this example, for example, they also have Picard rank 1, and I mean, it all does. You also can get some kind of derived equivalence there, and I suspect there is a mirror phenomenon of the same type. But there also, there's gazillions of Calabi-Yaus overall, and most of them don't give me anything like that. So.
So
Are there examples of like Mendelian variety is dual, or the difference is insulated by a power of L?
Yeah, so I don't. Yeah, see, that's right. So in those cases, somehow don't expect, and there's no obvious reason for why it would be annihilated. Right. So somehow, I feel that if you end up trading one fundamental groups, then you get a problem, right? There are examples of Christian Snell where you have derived equivalent Calabi-Yau varieties. They differ by taking a quotient, and there I have absolutely no reason to expect that their difference is annihilated. You know, so it's very much, it's a very young story, so you can expect lots of surprises, so who knows?
Yeah, that was my question, and I want, if I can, because it builds on what you're asking. I was curious about the fundamental group, right? Does it?
In this case, these are simply connected.
Yeah, they're all simply connected, but in general, would it give you a hint, right? For example, the opinion variety will give you a no-go theorem.
Yeah, I mean, yeah, right. I mean, I don't know. Right. I'm not sure. That's actually that's a question. I wonder if the class of the in the Grothendieck ring recovers the fundamental group. That's a good question.
Right,
I don't know.
I'm debating against quotients, right?
I'm not sure. Yes.
One more question. I guess we have a little bit of time. Yeah.
You mentioned a connection with mirror symmetry.
Yes.
Is there anything general there that you feel?
Well, I mean, they have the common mirror, and that physically suggests that you have equivalent direct categories. I don't know if physics suggests anything when it comes to the Grothendieck ring. I sort of doubt it.
You have a question? Raise your hand. Yeah, okay.
Can you expand on other zero dividers in the Grothendieck ring?
Yeah, I mean, I think it's just as messy as you would think of. I mean, somehow. Yeah. I mean, I really don't expect. I mean, yeah, I'm sure there should be lots of different zero divisors. But even, I say even any small progress on Grothendieck ring is already worthwhile. If it would be, to me, seems completely implausible that one could really understand that mod L squared, for example. But even if you do something in between mod L and mod L squared, that's already going to give you some really rich invariants of algebraic varieties. So I don't know.
Nilpotence and
yeah, I mean, I would expect to have nilpotence, but even in this case, I know that times L to the 6 is 0. As soon as if times L is not 0, then that's a nilpotent. I have no way of proving that times L is not 0, but I have no way of proving it is. So I would expect nilpotence. I really would.
No more questions? So let's thank the speaker again.